In section 3.6, we talk about polynomial and rational inequalities. So a polynomial inequality is any inequality that can be put into one of the forms. F of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, and f of x is greater than or equal to 0, where f is a polynomial function. And so how do we solve these? The x-intercepts of a graph are sometimes called boundary points, indicating the boundary between where the graph lies above the x-axis and where the graph lies below the x-axis. So our procedure for solving these is first you want to express the inequality in the form f of x is less than 0 or f of x is greater than 0, where f is a polynomial function. So all that means is we want to have 0 on one side. Then you want to solve the equation f of x equals 0. These real solutions are going to be your boundary points. We're going to locate these boundary points on a number line, thereby dividing the number line into intervals. We're going to choose one representative number called a test value within each interval and evaluate f at that number. If the value f is positive, then f of x is greater than 0 for all the numbers x in the interval, and if it's negative, then f of x is less than 0 for all numbers x in that interval. We're going to write the solution set, selecting the interval or intervals that satisfy the given inequality. Now just remember that this procedure is valid if we replace it with a less than or equal to, or greater than or equal to. However, if the inequality has that equal to bar underneath, then we need to make sure we include those boundary points in the solution set. So let's go ahead and try one of these. Let's solve the polynomial inequality 9x squared plus 3x minus 2 is greater than or equal to 0, and then graph the solution on a number line. We will express the solution set in interval notation. So this already has the 0 on the one side, so it's in the correct form. So the first thing we want to do is find those boundary points. And so we want to set 9x squared plus 3x minus 2 equal to 0 and solve it. So we can't factor anything out for GCF, so let's go straight to the AC method. That's 9 times negative 2, which gives me negative 18. And we'll have to have a plus or minus. And so our factors of 18 are 1 and 18, 2 and 9, and 3 and 6. And so which combo is going to get you to positive 3? The negative 3 plus 6 will give me positive 3 that I'm looking for. And so we bring the 9 down into both and we split the x's. We got 9x minus 3 and 9x plus 6. And we want to divide out whatever they have in common. So we have a 3 in common in the first one and in the second one. And so we end up with 3x minus 1 and 3x plus 2. Let's set each of these equal to 0. 3x minus 1 equals 0. And 3x plus 2 equals 0. And so this is going to give me x equals 1/3 and x equals negative 2/3. So those are your boundary points. That's what we are going to plot on our number line. So let's draw a number line. And we've got negative 2/3 over here. And we've got 1/3 over here. we need to pick some values in each interval to test. And it doesn't matter which one. You can just pick easier values to test. So let's pick the test point -1. We can pick 0. And we can pick 1. I'm just picking numbers that are easy to plug in. And so we want to plug in each value and see if we get a true or a false statement. So we've got 9 times -1 squared plus 3 times -1 minus 2, and that should be greater than or equal to 0. Well, this ends up giving me 9 times 1 minus 3 minus 2, which is 4, and 4 is definitely greater than 0, so this is a true statement. And since it's true, we want to make sure we shade in this region. What about 0? We've got 9 times 0 squared plus 3 times 0 minus 2. And that needs to be greater than 0, but those zeros are going to end up canceling those terms, and we just get -2 is greater than 0, which is not a true statement. So we don't want to shade there. And then we can plug in 1. We've got 9 times 1 squared plus 3 times 1 minus 2 is greater than 0. Well, that's just 9 times 1 plus 3 minus 2. And this ends up giving me 10, which is definitely greater than 0. And so we want to make sure that we shade in that region. And so because this was greater than or equal to 0, we want to make sure that we use brackets to include those boundary points. And so in interval notation, this comes from -infinity all the way up to -2/3. And then we use a bracket, and also from 1/3 to +infinity. Why don't you go ahead and pause the video and try example number 2 on your own. Alright, so for example number 2, we want to solve the polynomial inequality x cubed plus x squared is less than or equal to 4x plus 4, and then we're going to graph the solution set on a real number line and express the solution set in interval notation. So the first thing we have to do is we need to set it equal to 0. So we're going to move all the terms to one side. So we need to subtract 4x and subtract 4. And so we get x cubed plus x squared minus 4x minus 4 is less than or equal to 0. Now, because we have 4 terms here, we're going to factor by grouping. So we want to split this down the middle. We can take out an x squared term, and we're left with x plus 1. And remember, we need to have x plus 1 on the other side for this to work. And so what we need to put in the blank space is a -4. So we get x squared minus 4, and we get x plus 1. But x squared minus 4 can be broken down because this is the difference of squares. And we end up getting x plus 2, x minus 2, with that x plus 1 equals 0. So setting this equal to 0 to find those boundary points, we get x plus 2 equals 0, we get x minus 2 equals 0, and x plus 1 equals 0. And so we end up with x equals -2, x equals 2, and x equals -1 as boundary points. So let's put those on a number line. So we've got -2, we've got -1, and we've got 2. And so we want to find numbers that we can test. So I'm going to pick -3 for my first one. We got to pick something in between -2 and -1, so -1.5 would work. Between -1 and 2, I'm going to pick 0, and the last interval, I'm going to pick 3. And so let's plug these values in. We've got -3 squared plus -3. I'm sorry, -3 cubed plus -3 squared minus 4 times -3 minus 4 is less than or equal to 0. And what we end up getting is -10 is less than or equal to 0, which is a true statement. And so we want to shade in this region. Plugging in -1.5, -1.5 cubed plus -1.5 squared minus 4 times -1.5 minus 4 is less than or equal to 0. Well, that ends up giving me 0.875, which is not less than or equal to 0. Plugging in 0, we got 0 cubed plus 0 squared minus 4 times 0 minus 4 is less than or equal to 0. And that simplifies as -4 is less than or equal to 0, which is a true statement. And so we want to make sure that we shade in this region. And the last test point, we got 3 cubed plus 3 squared minus 4 times 3 minus 4. And that simplifies to be 20, which is not less than or equal to 0, and so we will not shade in that spot. So again, we have that equal to part on the inequality. It's less than or equal to 0, and so we need to make sure we use brackets. And so we have brackets on that -1 and the 2. So in interval notation, we have -infinity to -2 with the bracket, and then we also have from -1 to 2. Now, what about rational inequalities? So a rational inequality is any inequality that can be put into one of the following forms, and this is going to look really similar to what we just did. The only difference is that f is a rational function. And so we can find the x-intercepts by setting the numerator equal to 0. We can also determine where f is undefined by setting the denominator equal to 0. So let's solve the rational inequality. Negative x minus 3 over x plus 2 is less than or equal to 0. We're going to graph it, and then we're going to express the solution set interval notation. So let's find our x-intercepts. We're going to set that equal to 0, the numerator. So negative x minus 3 equals 0. That's going to give me that x equals negative 3. We are going to have a bracket on this because it's less than or equal to. Let's find out where it's undefined. And we do that by setting the denominator, x plus 2, equal to 0. Well, that ends up giving me x minus 2. Because it can't be negative 2, that would make it undefined, we have to use a parenthesis. Because that's going to cause a 0 in the denominator. So let's draw our number line. We've got negative 3, and we've got negative 2. And we need to find some test points. So let's go ahead and pick negative 4. We can pick negative 2.5. And we can pick 0. And so let's plug those into the function. That's negative 4 minus 3 all over negative 4 plus 2 is less than or equal to 0. Well, what we end up getting, negative 4 is positive 4, minus 3 is 1, and then negative 4 plus 2 gives me negative 2, and negative 1/2 is definitely less than 0. So we want to make sure that we shade in this region. We're going to do the same thing with negative 2.5. So negative 2.5 minus 3 all over negative 2.5 plus 2 is less than or equal to 0. But that's going to end up giving me negative 0.5 on top and negative 0.5 on the bottom, which is really just positive 1. And that is not less than or equal to 0. In the last test point, we've got negative 0 minus 3 all over 0 plus 2. Well, this ends up giving me negative 3/2, which is definitely less than 0, and so that's a true statement, and we want to shade here. Now we have to be careful of the signs. On negative 3, we said we can use a bracket, but on negative 2, we have to use a parenthesis. And so my solution set would be from negative infinity to negative 3, and then from negative 2 to positive infinity. Negative 3 gets the bracket, and negative 2 gets a parenthesis. And the last part is applications. So quadratic functions can be used to describe objects that are falling. The position function for a free-falling object near Earth's surface can be given by the following. So an object that is falling or vertically projected into the air has its height above the ground, s of t, in feet, given by s of t equals negative 16t squared plus v naught of t plus s naught, where v naught is the original function, or the original velocity, which is the initial velocity of the object in feet per second, and t is the time that the object is in motion in seconds, and s naught is the original height of the object in feet. So divers in Acapulco, Mexico dive headfirst at 8 feet per second from the top of a cliff 95 feet above the Pacific Ocean. During which time period will the diver's height exceed that of the cliff? So let's go ahead and write our function. So s of t equals negative 16t squared plus our v naught is the original velocity. And so that's going to be that 8 feet per second that it falls. So that's 8t. And then s naught is the original height. Well, the original height is 95. We want to know during what time period will this height exceed that of the cliff. Well, the cliff is 95 feet. So we want to set this greater than 95 to solve this equation. So let's go ahead and set this equal to 0 so we can solve it. And so that means we are subtracting 95 from both sides. And so it's actually going to end up canceling on both sides. And we get negative 16t squared plus 8t is greater than 0. Let's go ahead and find those boundary points. So we need to set this equal to 0 first. And so factoring, we can pull out a greatest common factor of 8t. And we're left with negative 2t plus 1 equals 0. And setting both these pieces equal to 0, we got 8t equals 0, and we've got negative 2t plus 1 is 0. And so we end up getting t equals 0 and t equals 1/2. And so we want to plot those on our number line. So we've got 0 and we've got 1/2. And we need to pick our test points. So I'm going to pick negative 1. I'm going to pick 1/4. And I'm going to pick 1. So we got negative 16 times negative 1 squared plus 8 times negative 1 has to be greater than 0. But we end up getting negative 16 minus 8 is definitely not greater than 0, so we aren't going to shade there. Let's try 1/4. We got negative 16 times 1/4 squared plus 8 times 1/4. And that's supposed to be greater than 0. Well, that simplifies to be 1, which is definitely greater than 0. And so we want to shade in that region. And then we need to test out 1. So negative 16 times 1 squared plus 8 times 1 greater than 0. but that ends up giving me -8, which is not greater than 0, so we will not shade here. And because this is strictly greater than 0, we will be using parentheses for both. And so that means the diver's height is taller than the mountain between 0 and 1/2 seconds. So not very long.